Welcome to this webinar. We will get started. This webinar is hosted by the IBPSA Education Committee. We identify education and training needs throughout the building performance simulation community, including academia, private sector, and the government. Initiate, develop, encourage, and/or coordinate new education materials and methods. Offer training sessions to non-members as well as members. Promote the development and the sharing of best practices in building performance simulation education. If you have any questions during the live session, please use the Q&A icon to submit them. Now, I'd like to introduce today's speaker, Beausoleil-Morrison. Ian is a professor in the Faculty of Engineering and Design at Carleton University in Ottawa, Canada. He was the president of the IBPSA from 2010 to 2015 and received the Distinguished Achievement Award in 2021. Over the past 3 decades, he has researched, developed, and validated models and simulation tools for buildings and energy systems. He is the author of the textbook, Fundamentals of Building Performance Simulation, and he co-founded and has served as the co-editor-in-chief of the Journal of Building Performance Simulation, which launched in 2008. Welcome, Ian.
Thank you very much, Guan Chu, and thank you for the introduction and for the opportunity to present today. I'm just going to turn my screen sharing on. Okay, so today I would like to present on the topic of, sorry, just going to make sure, is my screen sharing working correctly? Perfect. I'm going to talk today on learning building performance simulation fundamentals. And this is something that I've been grappling with for most of my career. I've had the opportunity to teach building performance simulation to many different types of audiences, practicing engineers and architects, university students, professionals working in the domain. And I've had the opportunity to try out a lot of different techniques, and some work better than others. I've refined them over the years, and I've feel like I've got to the point now where I have something that can work fairly well for teaching what I call the fundamentals of BPS. So what I'm going to present today is really a series of methods that I use in my own teaching, in my own university teaching and professional development training. And I've encapsulated this in a book that the first edition of the book was published a few years ago, and the second edition is at the printers right now and will be out within the next month. So that's what I'm going to present about today. The American Institute of Architects has produced a very interesting guide called The Architect's Guide to Building Performance, and it really introduces what BPS is and how it can benefit the design process. And in this document, they make a distinction between the types of BPS analyses that commonly performed by architects, such as things like massing and orientation, solar and shading, daylighting and glare, these types of analyses typically made at the early stages of design. They distinguish that from the types of analyses that are conducted by what they call BPS professionals or BPS specialists. These are people who are primarily conducting simulations in their professional role, most typically engineers, but not always. Sometimes it's an in-house resource in an architecture firm. Sometimes it's a contracted out resource. Sometimes it's a member of the engineering consulting team. And so really what I'm talking about here today are the fundamentals that are necessary to be learned by the people who want to be BPS professionals. But I think it's also important these things are to be understood by those who are working with BPS professionals so that they can understand the benefits of the BPS technology and also, importantly, the limitations. So we have a lot of BPS tools available to us nowadays. And this situation has changed drastically. I'm just showing a few here. We have IES-VE is a commonly used one, eQuest, Design Builder, Green Building Studio, lots of integrated, sophisticated software packages that allow the user to define the detailed geometry of the building, the materials that make up the building, describe the activities that are conducted within the building, describe the HVAC systems that are used to condition the building, commission the simulation analyses, what are commonly called by the calculation performed, what's commonly called a simulation engine, and then echo the results back to the user, produce the results back to the user. So we have many, many sophisticated software packages. And there's some, I think, fairly bold and I would say unsubstantiated claims made by some of these package developers. Things like you don't have to be an expert to use it. No previous experience with BPS is necessary. Energy analysis made easy. And I don't think conducting BPS analyses is easy. I think we often go awry by assuming that it's an easy thing to do. We do have a lot of learning we have to do in order to become proficient at using these tools. So yes, great user interfaces, great sophisticated packages, worlds beyond what we used to deal with. This is when I started working with BPS, this is the kind of interface we had with a BPS tool. This is from the DO2 program. It was basically a text-based input. You would have to write in these keywords and numerical values that went with that keywords and simply perform an analysis after that. So no graphical interface to allow you to define geometry, no sophisticated results analysis capabilities. And I was lucky because the people who were working on this a few years before my time were using punch cards. So we've come a long way, but we still have a problem in that it's not easy to use these tools. I like to refer back to a paper that Linda Laurie worked on 40 years ago now, in which she argued that the user is the greatest source of uncertainty when we're conducting BPS analyses. When we're working with BPS, we have software tools that are trying to represent all of the significant physical processes happening within the building. And by necessity, these models have to simplify things. We have to simplify things, simplify the physical processes to make it resolvable by the calculation engine. There's also potential that some of these models would be coded incorrectly into the simulation tool. So these are all possible sources of error. But what they were arguing 40 years ago was that, yes, those are possible sources of error, but it's really the user is the biggest source of error. And despite the fact that we have now sophisticated software packages, I think what Linda Laurie was saying 40 years ago is still pertinent today. The user is still the biggest source of uncertainty in using these tools. Here's a little experiment that I've run with my own students to illustrate that fact. What we have here is each one of these bars represents a simulation prediction made by one of the students taking my course at university. Now, the vast majority of students taking this course have never used a BPS tool in their life. They've never thought about BPS. They've just signed up for the course. They want to learn about it, but they have no prior experience. And within 2 weeks of starting the course, all of them are able to execute a simulation program to predict some results. We're dealing with a very simple building, just a shoebox representation of the building, but they've gone through the learning process where they understand how to interact with the software. They know how to push all the buttons and pull all the levers to get it to produce some simulation results. And what we have here, these blue bars are representing their predictions of space cooling load. And this is where this green box here is showing where the correct result should be. And what we can see from this is a lot of these students are under predicting the cooling load. A lot of them are drastically over predicting the cooling load. Not that many of them are falling within the expected range. So it's not their fault. They're just at the early stages of learning. Some people might say it's my fault. I didn't teach them well, but the point of this exercise was to get them up the learning curve quickly so that they could operate the simulation tool. And that's the easy part, training someone to operate one of these simulation tools. But for them to learn to understand really what the simulation tool is doing and how to use it effectively, that's a much longer process. And we tend to often neglect that the fact that we need to do a lot of learning and a lot of training before we're proficient at using these tools. So this was a little experiment. Again, all of these people within 2 weeks of starting the course are able to operate the tool, but these are novice users. Well, we look through the literature and the building performance simulation literature, and we find lots and lots of examples of cases like this, but more experienced users making similar issues. This was a study almost 30 years ago from Électricité de France, and they had 12 people using their simulation tool, Clim 2000, and they were all given a common set of building drawings and specifications and asked to make some predictions. And we saw that many of those users made some fairly fundamental errors, and we had a lot of prediction inaccuracy. So a result that's not too different from the novice users in my course. Here's another example from California from about a decade ago. In this case, all 12 of the people making predictions here are BPS professionals. So these are people who earn their living conducting BPS analyses. And they were given a common set of plans and specifications on a building and asked to predict gas consumption and electricity consumption. And these graphs are representing their monthly integrated predictions of these gas and electricity consumptions. You can see the spread in results here. Again, we have a significant variation between users. In some cases, this might be errors that the users made. They might have made some assumptions about input data that were inappropriate. But we again see it's the user that's the main source of uncertainty. Here's another example from an International Energy Agency annex that was reported in the Journal of Building Performance Simulation. And in this case, we have measured results, this dark black line here, that's predicting the heating output in a research facility over time. And the users in this case were mostly PhD students who spent weeks and weeks, if not months of time, trying to accurately represent this building. And you can see we have a lot of variation between users again. So what's going on here? Is it the tools that are the problem? Is it the models within the tools that are the problem? Well, I argue that BPS is very complex, and BPS is very complex because buildings are complex. The physical processes happening within the buildings are highly uncertain. They're being excited by uncertain boundary conditions, meaning uncertain weather conditions, occupancy patterns, usage behavior, whether blinds are open or closed, whether lights are on or off. These all have an impact on the physical processes happening within the building. And as users of these tools, we have to decide what are all the physical processes that are happening in the building, which ones are the most significant, which ones are important to consider in this particular case, and how do I best represent them? What are the modeling methods used by my simulation tool? What are the optional modeling methods used by my simulation tool? Which one should I use in this case? And for this reason, I think it's very easy for users to feel overwhelmed with all of these decisions that they have to make. And in many cases, these tools provide users default methods and default input data that sometimes we accept and we don't fully understand the implications of these choices. So I think it's very important that users understand what their BPS tool is doing with the input data they provide, understand which of the input data is going to have the most impact, and put their efforts, because time is a limited resource, put their efforts on the things that matter the most. So this is why I argue that understanding the fundamentals of what these tools are doing internally, how they're using the data that we provide is essential. So in the teaching that I'm doing, the learning that I'm encouraging, it's very different than training somebody how to operate a piece of software. As I argued a few minutes ago, it's actually really easy to teach somebody how to operate a piece of software, even a sophisticated tool like a BPS simulation tool. But it's quite another matter to teach them or for them to learn to understand how those tools are operating and what the limitations of those tools are, what the default methods in the tools are. So they really need to understand, I argue that they need to understand some of the theoretical basis of the tool. And we need to train them or prepare them for that in a way that is accessible. So as I mentioned before, I've developed my teaching methods over the years. I regularly teach courses at the university level, mostly engineering students. I've also given professional development courses where I've used this method. And I've written this book called The Fundamentals of Building Performance Simulation that encapsulates this teaching approach. So it can be used as a self-study guide as well, as the way it's structured. So it's really focused on the building thermal processes and HVAC processes happening within the building. It doesn't presume any prior knowledge of BPS. So you don't have to have any BPS experience or knowledge before you start learning using this as a guide. You do have to have some basic background in heat transfer and thermodynamics, university undergraduate level knowledge in these areas is sufficient. A little bit of understanding of psychrometric concepts, and then some understanding of HVAC terminology and common configurations, but not in-depth knowledge of HVAC design. So the way the book is structured and the way that I teach people to understand the fundamentals of BPS is the same. There's a number of chapters in the book, and each chapter is dedicated to a particular topic. So there'll be a topic, say, on convective heat transfer at internal building services, a topic or chapter on internal sources of heat gains and moisture sources, another one on ground heat transfer. So in each one of these topics, there's really four main modes of learning. There's some theory presented, and the book is not trying to be a compendium of all of the modeling methods used in BPS tools. It's illustrating some of the major ones that are used, and it gets mathy in some places, but it really I avoid using too many mathematical descriptions. It's really trying to use the math when necessary to describe the theory. And importantly, every chapter has simulation exercises. So I feel it's very important that people start using these simulation tools immediately and use the simulation tools in concert with studying the theory so that they develop the practical experience as well. And that helps to better understand the theory and provides more motivation for understanding the theory, because the theory on its own is pretty dry and boring. So they conduct simulation exercises related to that topic. And then in my teaching, I always do what I call a simulation autopsy. And that's where the students will present the results together and we analyze them collectively, and we try to understand why one student is predicting high and another student is predicting low. What were the different choices that they made? What were the different algorithms that were exercised? And then after conducting that, we reflect upon all of these things and go back and better understand the theory. That's the hope. So we finish a topic, and then we move on to the next chapter of the book and study the next topic. And the book is broken down into different parts. So there's a part that focuses on all the heat and mass transfer processes happening within the building. So things like radiation exchange between a ceiling and a floor, convective heat transfer happening at internal surfaces, internal sources of heat, etc. Everything that's happening within the building, that's in one part of the book, and there's a separate chapter on each one of these topics. And then there's another part that focuses on the heat transfer processes happening from the outside of the building to the exterior environment, things like long wave radiation to the sky, heat transfer to the ground, etc. Another part that focuses on what's happening within the building envelope, air infiltration through the building envelope, transient heat transfer, conduction heat transfer through the building envelope. And then another part that focuses on HVAC systems. So each of these parts is broken into chapters. Each chapter focuses on one of these particular topics, but they all have a common structure. They all introduce some basic theories. And again, it uses math where necessary, but it's not trying to overwhelm the reader or the user with too much theoretical concepts, but enough so that they can really understand what the tool is doing internally with the data they provide. It's written in a tool agnostic way, so this is not written around one particular simulation tool. It really relates to the methods used by many of the common simulation tools available to us today. Talks about strengths and weaknesses of these methods. And then there's additional readings and guidance to additional readings for people who want to delve into much more detail. And importantly, these simulation exercises inside each chapter. So I give you a quick indication of the kinds of theoretical presentations that are given in the book when it comes to long-wave radiation exchange between internal surfaces, say between this wall and this wall. It explains some of the basics of radiation heat transfer. So again, if somebody's taken an undergraduate level course in heat transfer, this is a bit of repetition. It talks about emission of radiation from gray bodies. It introduces enclosure analysis, and it shows the mathematical development. But the main point of this is so that the user can see there's some important parameters in these equations that are provided by the user. Things like geometrical view factor between surfaces, the emissivity of material properties. So the user can see the data that they provide to the simulation tool, how it's used in the calculations and what impact that might have on some of the predictions. Here's another example looking at solar energy absorption on external surfaces. So it starts with some basic concepts about solar angles, angles of the Earth rotating around the sun, how those angles vary over the course of the year. Talks about sky diffuse radiation, shows how all sky diffuse models are empirical in nature, and then talks about the different models that could be available in different simulation tools. So again, the user develops an appreciation for what some of their modeling choices are having on the calculations performed. So most of the chapters in the book they all have simulation exercises. Most of them are operating on very, very simple buildings, just shoebox representations. So one that is representative of light frame, light structure, residential construction, and one of a heavier construction, more high-rise construction, but a single zone. And these base cases are written again in tool agnostic ways, so they can be conducted by any simulation tool. And in my own teaching and teaching of others, they've used a number of different simulation tools for conducting these exercises. So I'll give you an idea of some of these exercises. Here's a couple for example, in the chapter on how solar energy, how we predict the absorption of solar energy at internal building surfaces, like a floor surface. There's an exercise where the user makes a simple change, just changing the solar absorptivity, which is a user input of a floor surface. And here's a result from one student showing that energy that's absorbed on the floor surface, how it varies over the day. And we can see these two lines here representing two cases, one where we've just changed the solar absorptivity of the floor. So we can see when we increase the solar absorptivity, we predict much higher solar radiation absorption on the floor. That makes sense. It relates back to the theory. It makes sense why that's happening. But then we look at how much heat is required to condition that building over these two simulations. You can see these results are almost the same. And at first that might seem counterintuitive that we've made a significant change to a user input, but it's had very little impact on a parameter that we're interested in, how much energy is required to heat that space. And when I conduct these simulation autopsies, we always have a discussion around that. Why is that happening? And students relate it back to the theory they've studied in earlier chapters, and they realize that for this particular building type anyway, a significant change in the solar absorptivity of a surface has minimal impact on a parameter they're really interested in. And that's a useful result for them to store in their minds for future reference. Here's another example where we're looking at the chapter on air infiltration, and we're looking at each one of these groups of bars here as a different student. And you can see we're trying two different methods here, two different commonly used methods of treating air infiltration. Just ignore it, or we prescribe a fixed air infiltration rate. Both of them are not very accurate representations of reality, and we can see that each one of these students is showing that has a significant impact on our predicted heating load. And then we try a couple of more sophisticated modeling approaches, and we see, well, those also have a pretty big impact on predicted heating load. And the takeaway from this is that treating air infiltration has much more of an impact on a result we're interested in, a space heating load, than defining the solar absorptivity of building materials. And that's a result that I want students to retain for future reference. So when they're faced with simulating the performance of an actual building, they realize where they should be placing their priorities, where they should be investing that precious time resource. All right, so most of these chapters are operating on these simple shoebox buildings, and we're varying one thing at a time. I think it's very important now to put all of that together to try and predict the performance of an actual building, which is obviously way more complex. We have now to face a lot of decisions about, do I spend my time defining the geometry, or do I spend my time trying to model air infiltration or predicting the solar reflectivity of the snow surrounding the building, et cetera, et cetera? Where do I place my efforts? So the book describes this. This is an unoccupied research house on our university campus. There's a number of photographs that are provided so you can understand the construction practices, the materials that are used to make up the building. There's photographs showing detailing of insulation placement, for example. There's issued for construction drawings, as-built drawings that showed accurate dimensions. And the user has to look at all of this and decide, how do I represent the performance of this building? Where do I place my efforts? And here's a couple of examples of students who took very different approaches. Here's one who decided to represent the geometry as faithfully as possible, representing all of the interior partition walls in their exact location and their thermal massing, et cetera, et cetera, et cetera. And another student who took a very abstract representation of the building, lumped all of the windows together on the main floor into one, a simple rectangular representation of the building. So obviously much less effort to produce this version on the right than the one on the left. And that's an advantage. The students will learn from each other by seeing the impact of some of these modeling choices. And then we have measured results to compare against. So I'll flip back to the picture of this building. You can see right here, there's a pyranometer mounted on the external wall. In one of our comparisons, we're going to compare our simulation predictions to measurements of that pyranometer. So that thick gray line here is the measured solar irradiance on the outside of that south-facing wall. And then each one of these dashed lines is a student prediction of that using their simulation tool. So we look at these results together, and then we try to dissect them and understand by exchanging ideas why this student up here with the yellow line predicts so much higher solar irradiance. What were the decisions that that student made that influenced their modeling prediction? And the goal is to collectively learn, from that experience of your own experience and the experience of others. Here's another example where we're trying to predict over a 10-day period the internal temperature in one space, the second story of the building. And again, the thick gray line is showing that temperature as the building is free floating. There's no heating or cooling at this point in time. And again, we see each of the dashed lines is a different prediction by one of the students. And again, we learn from that. Why did one person predict lower temperatures, another person predict higher temperatures? There's also another culminating trial that focuses on HVAC systems. So this is another building on our university campus where I have access to measured data in this building. It's a conventional construction with an atrium space, and we have detailed information on the HVAC zoning strategy, issued for construction drawings, detailed information on the materials that make up the building envelope and the structure. And again, people have to take that information and decide where to place their effort. A representation of the HVAC systems. This building has an conventional air-based VAV type system. And we're trying now to predict the performance, particularly in the HVAC system in this case. So we have measured results that are looking at some of the terminal equipment. So this is the airflow through a VAV box serving one particular office. Can we predict that well? Why can't we predict it well? What are the challenges in predicting that airflow rate? We also have measurements from within the air handling system. So the airflow through the variable volume supply fan, the fraction of outdoor air introduced into the system, the heat output from the heating coil. So these are all parameters that would be of interest in a simulation-based study. So again, the point of all this is it's a learning exercise. How do I use this particular case to better learn the use of a simulation tool? How do I take all the knowledge on the fundamentals that I've gained so far and put it together to predict performance of an actual building? So, as I mentioned, I've tried lots of things over the years. Some things worked well, some things didn't. And what I've tried to do in this book that I've authored is to encapsulate all of those learning processes that I think are critical for anyone who wants to be a BPS specialist or a BPS professional to really understand the fundamentals. It's used in a number of universities for teaching courses. It's used in professional development courses as well. As I mentioned, I first published this about 5 years ago, and the second edition is currently with the printers. It's going to be available in about 3 or 4 weeks from now. And the second edition has some major additions to HVAC, because what I heard back from those using the book is that they wanted more treatment of HVAC systems and lots more simulation exercises and culminating trials. Because again, the feedback I get is those experiential learning tasks are a very important part of the learning. And I just want to mention that this is a book that is endorsed by IBPSA. And importantly, it's tool agnostic. So you can pick up any simulation tool of your choice to use this as a learning resource. And then just finally, there's a couple of additional articles if you're interested in more details of learning approaches or teaching approaches related to BPS fundamentals. There's a couple of articles that I've authored that you might be interested in. And with that, I will conclude my presentation.
Thank you, Ian, for the insightful presentation. We are now moving into a panel discussion. We have 3 experts from the AIA Building Performance Leadership Group: Jessica Saravia, Will Babbington, and Drew Crawley. Welcome, and thank you all for being here today. Following up on Ian's talk, my first question is, in practice, what are the main barriers that prevent professionals from using building performance tools?
I'm up first, right?
Yes, please.
Hi. I will dive right in and say cost. I an architect who works mostly on hospitality projects, and our biggest struggle can be working with owners and educating them about the benefits of things like energy modeling and understanding building performance at a level like you're talking about. There's still quite a bit of working to code minimums and meeting energy code at a prescriptive level and things like that in private kind of like design driven work that comes to play in our practice. So it comes with looking at payoff over time in terms of systems and things like that. And I think there's definitely a place for energy modeling and building performance simulation when it comes to deciding on various HVAC systems and things like that for the building, that you can make the pitch that it's like, hey, this is going to save you money over time if we can find more efficient ways to heat and cool the building, or better ways to insulate your envelope, or things like that. But it still can be a hard sell with upfront costs for those design fees and things like that. So that's kind of where we end up with difficulties.
And so in terms of what I do as a day-to-day, my background really is we're an enclosure designer. So an architect would hire us to help further that design, kind of like Jessica was alluding to there. So we're, as part of our day-to-day, we're doing modeling, structural sizing, taking into account thermal bridging, looking at that condensation potential that's associated with thermal bridging as well as moisture transfer. So that's what we get there, but really in terms of preventing us to have a greater impact, I would say it's maybe not getting it actually in the design more and more. It's more prevalent, we're seeing, but it's using it correctly. Starting very early, and not just very early, but gaining a sensitivity handle on all right, for this particular project, do I need to focus more on the roof? Do I need to focus more on shading for this building type, etc.? So we'll see more and more whole building energy modelers being brought in on projects, but oftentimes it's just to validate assumptions and see where we're at further on in the process where they're missing out on some impact that they could have much, much earlier in the project and overall.
And I work on the opposite side. I work for a software company. So our focus is really trying to make the tools easier to use. And as Ian alluded, that the data that we need to support that is really the critical thing, and getting that as much information to users in a way that they can use it very quickly.
Yeah, I think on the optimistic side, we see more and more use of BPS in building construction process, but unfortunately, I'd say the majority of applications are still, as Will is saying, happening very late in the design process. In many cases, they're being used simply to demonstrate compliance with codes and standards, and it's not influencing the design process as much as it could. So I think we still have a big challenge to demonstrate the power of BPS. And I think things like the AIA guide are very useful in demonstrating some of the potential of BPS, how beneficial it can be on some of the design decisions, and especially the decisions that are made earlier in the design process. So I think we're still in the process of this cultural change. And, you know, as Jessica was saying, the cost is a big driver. Getting a client to pay for that early stage analysis, motivating them is, I think, often a challenge. So I think the more we can demonstrate, the more success stories we have to demonstrate the power of BPS and the benefit it has in the design process, the better.
Right. Thank you. And I have a second question. As we know, technology is evolving very quickly. How might emerging technologies, such as AI, impact building simulation?
This is probably a better question for Ian and probably Drew even than for me, but this is my like dream wish list for AI and building simulation. I mean, you know, I think as designers, we all hopefully know that AI, you know, we don't need AI to design buildings for us. Like, I think, you know, hopefully we all realize that more, you know, shiny computer renderings are not what the world needs. It's definitely not that type of heavy lift that I'm looking for out of artificial intelligence. I want people to do the designing, and I would like for artificial intelligence to quickly run through scenarios for me of you know, cost estimating against different types of systems, different types of orientations. It would be fantastic for me. And I'm sure this is, you know, still, it's always going to be like garbage in, garbage out, right? Like Ian was saying, like whoever is doing the simulation or you know, giving inputs into the system is going to be the person that ultimately has the most control over what you're getting is in terms of output. But what would be ideal is to, you know, be in concept or be in schematic design and say, these are our priorities in terms of like, you know, cost of HVAC system, or thinness of exterior wall, or you know, we have money to spend on glazing, but not this X, Y, or Z, and then say, have, you know, AI spit out like, hey, if you were to orient the building in this direction, or take out this corner, or simplify your massing in this way, or add 2 inches of exterior insulation here, or add more solid wall and get rid of glass there, and give you options and say, you know, this is going to reduce your energy out, needs for your envelope, or, you know, in your envelope will save you energy needs over the course of your building. You know, it'll offset the cost of your electrical bill in 5 years or whatever by the cost of this extra fiberglass clip or whatever you need to add. And that would be, again, like also the sales point for the owner, right? Like you could say quickly, hey, look, I know we're going to spend more money on triple pane glass, but, you know, if it all goes well, this is going to pay off and then some over the course of the life of this building, and this is the right thing to do. So that's what I would love for AI to do for me, is to give me more ammo and, you know, eliminate the need for contractor pre-con services. I mean, that's very optimistic. I'm not sure that would happen.
Yeah, so for me, like Ian teed up beautifully as far as one, knowing what's under the hood, obviously, of all these great new engines, if you will, that are out there on the market and coming through, and tools at our disposal. I've become more and more concerned, I think, with the fuel that goes into those engines. So good data, like Jessica was saying, garbage in, garbage out. And I know it's a touchy subject. It gets into politics a little bit, but let's say climate data change. So is how I'll try to agnostically put it. But using like future and extreme weather data, trying to figure out, knowing what that good data is. In the past, it's like, all right, I got 50 years worth of data here to plug into this. We can get a good sense of what's going on. And with that trajectory kind of changing here and there, just keeping a good pulse on it, so we know what's going into those engines, if you will, and maybe kind of making that data a little bit I guess a little bit more reliable. I'm loving the technologies and gathering the data as we're going along real time. So instrumenting and validating what's coming out of these engines in particular. A lot of great research projects going on out there that are getting us closer and closer to that point. But it all helps us understand, you know, how much weight we put on those results that come out of those models.
I think AI is going to be really powerful for us, particularly looking for data, new sources, checking data, being able to look at it. We are working with a couple universities and even with our own software tools and different using AI and machine learning to acquire geometry. Even something as simple as Google Maps and the 3D buildings, and being able to take those tiled and convert that into something useful that can be done with simulation. We've done several projects on that recently. But having played with AI tools a bit in the last 6 months, you have to know when it's hallucinating. And they hallucinate a lot. They just kind of get lost and they just start making data up. And that's really where we're going to have to be very careful for a while.
Yeah, the three previous panelists have all made excellent points. The only thing I'd like to add to that is I think AI presents huge opportunities for this field and others, and even bigger risks. That I think all three have mentioned that we can't be overly reliant on the AI technology. And I think that's where the big risk is. How much faith do we put in it? It can be extremely useful at things like gathering data. It's quite tedious to take a building geometry and input it into a BPS tool. So it would be great to be able to harness AI for tasks like that, as Drew was describing. But there's a lot of judgment decisions that have to be made. And as Jessica was saying, we want educated people to be making those important decisions, not a black box somewhere. So I think we have to be very careful, but it does offer extremely great potential. We just have to be very careful about how we use it and not lose sight that we do need intelligent humans making the important decisions and being able to understand, as Drew was saying, when the AI tools are hallucinating, that we need to be able to make those decisions.
Yeah, right. Thank you. Let's see how it goes in the future. And we have many students and emerging professionals with us today. What advice would you offer them for learning about building performance and getting started in their careers?
Gosh, I would just say, don't be intimidated. All of this is can be intimidating, I think, if you let it. But try to let your curiosity take the driver's seat. And you know, if you're interested and curious, let that be your guiding force, and don't be afraid to ask dumb questions. I ask dumb questions all the time, and sometimes you get really interesting answers asking dumb questions. If you don't know the answer, then that means somebody else doesn't know the answer either, and no one has all the answers. So I think it's okay to step up and say that, and admit where you have gaps in knowledge, and that you're curious to infill those gaps, and offer what you have to others too. So yeah, I mean, I've had a lot of fun today, actually, just learning this stuff. You know, it's like I'm not an expert by any stretch, and it's been very interesting. And especially like Drew, I would love to hear him talk a little bit more about AI hallucinating. Like, that's terrifying and also very interesting to me. But yeah, no, it's you know, hopefully as designers and architects and you know, energy professionals and engineers, it's like you all have a long career ahead of you that's going to be evolving and changing in ways that we can't even imagine yet, which is great. It's part of what's great about being in this field. It's we don't know what's coming, and it's all there for our kind of learning and career growth and progress. So you know, it's not same thing every day, which is the exciting part, I think.
I think, yeah, Jessica just stole a few points, and Ian, the professor, obviously hit all those points that I initially gravitated to. But one thing, I'd say it's maybe not as technical oriented in all those beautiful equations. I mean, if you're in this field, you might gravitate towards that. But how I think you could make a bigger impact is learning how to communicate and filter and transfer that information. And whether it's graphics, a lot of good research out there that makes that point very quickly to a multitude of audiences, or kind of going back to the initial question of how to show your worth on a project. Obviously, owners, they're footing the bill. So translate those results into dollars or years in terms of replacements or whatnot. And it's, I don't know if you'd call it a soft skill that much, but it is really taking all those great numbers, great information, and conveying it to people in a meaningful way.
I agree with Will and Jessica. Getting out there, being curious, looking for ways to use the tools. But I also think that one of the key things is to start to dive in, to start using. Most of the tools have some tutorials and things like that. What I love about Ian's book, though, it is tool agnostic, so that you could use it for any tool. And learning how to query the tool and try to get results is as important as anything else, and understanding the insides of what's working, because that's going to affect what information you're able to get very, very much. So
yeah, all great points. I think as Jessica was saying, don't be afraid to ask questions. You'll have a whole lifetime ahead of you of learning. I've been working in energy simulation for almost 40 years now, which makes me feel really old. And I learn something new every day. We'll never know everything. So you'll just know that you're always going to be asking questions, and don't be afraid to ask what seem like naive questions. You're going to learn from that. There's lots and lots of resources out there. BPSA has a BPSA Education has a channel. There's a whole bunch of webinars that are posted online. There's conference proceedings available. There's journals. There's lots of books out there. There's tons of resources that you can use to support that lifelong learning. And the only other thing I'd like to add is, if you want to be a BPS specialist, I would suggest that you invest the time to learn more than one BPS tool. Don't be constrained by a single piece of software. There's dozens and dozens of really good packages out there, and they all have their strengths and weaknesses. So take the time and invest the energy to learn more than one. It'll really pay off in spades, I think.
Yeah. Thank you. And although we are almost at the end, we still have a few minutes left. I would like to pick up one question from the attendees. One question is, what's the common mistake your student or your team did in the simulation from your experience or class? Maybe we can give a quick, brief answer to this question.
There isn't a single common mistake. There's all kinds of very innocent errors. I was teaching a course a couple of years ago, and one of the I'm not going to out the individual, but one person taking the course had been working in BPS for 20 some years, and his simulation results looked really odd. And he made an extremely innocent mistake when he typed in the thickness of an insulation. Instead of putting 10 centimeters, he put 100 centimeters. That's a simple data entry problem. And we all do it. Those are common mistakes of just not doing enough scrutiny and checking of our inputs. But I've seen everything from the building facing the wrong way, a south-facing window facing north, using the wrong weather file. I mean, everything. And I don't mean to pick on individuals. I've made lots and lots of those mistakes myself. So, oh, you're on mute, Drew.
Drew, you're on mute.
yeah, the key. Thank you. The key is to knowing when it's wrong, or being able to diagnose it.
Yes.
But the thing that I found, I was working at a national lab years and years ago, and a team was doing a simulation of a building, and they couldn't figure out why they couldn't get the interior conference room above 50 degrees F or 10 C. Well, they had misunderstood how the tool used, and basically the ground was sucking heat out of the room faster than they could put it in. And they didn't know the shortcut that you had to use for that particular tool to get accurate ground heat transfer. So it's also understanding, as Ian said, the limitations of the tool.
Yeah, that's a really good point I'd like to build on. Is one thing I advise people to always do before they run a simulation is run a mental simulation. Think about, how do you expect that building to perform? What kind of temperatures are you expecting to see? What kind of heating or cooling loads are you expecting to see? Have that idea in your mind before you ask the computer to run the simulation. And if your simulation tool comes back with something that's radically different, like in Drew's case, he just mentioned this space that was underheated, then there's a pretty good chance that the problem is with your data input to the simulation tool. And the more experience you develop, the better your mental simulations become, the more accurate your predictions, and you're better able to scrutinize those simulation results. So that's a really important skill to build.
Yeah. Yeah, and I think related, maybe I'm echoing the same thing, but yeah, it seems like these tools allow us to go so much faster and cover so much ground and look at so many other opportunities. We get going so fast, even in our input and everything else, where we forget to look back. And I think those checks, I like that though, at the beginning, say this is my guess and test that hypothesis rather than trust that blindly and completely that analysis. All right, here's my result. Let's go. And remember, in structural engineering, people will put all your loads in the model and just a quick static check to say all the loads going through that building should equal and opposite the loads coming out of those reactions. And so often that would stop so many errors from happening. But yeah.
All right, we are almost at the end. Thank you all for joining us today, and a big thank you to our speaker and the panelists. For AIA members, please use the link in the chat or scan the QR code here to apply for continuing education unit. I will leave here for a moment. IBPSA education webinars will be posted on our YouTube channel, IBPSA University. We invite you to follow us there. In the meantime, you are welcome to join IBPSA as a student or a full member to explore academic resources and connect with the global community. Again, thanks, and we will see you at the next webinar.